shall we get going? So immediately after class, this is 1:45 on Tuesday, the person who runs the differential equations Twitter feed tweeted out this, which I thought was incredibly timely and helpful for what we're doing in class. And it says that knowing what is big and what is small is more important than being able to solve partial differential equations. And I love this quote. It's really hammering home exactly what it is we're talking about in terms of comparisons, dimensionless parameters, and finding a small parameter in your problem and understanding, especially with the last problem we did with the kind of nonlinear diffusion, the KPP equation, recognizing that what is small depends on what you're looking at in your problem. And so what is small might be that the nonlinear contribution of this diffusion problem, or that the effects of diffusion are small, and they lead to two different problems with two entirely different sets of solutions. I do recognize, however, that up until this point, we've done a lot of work to just kind of reconfigure equations, and it might seem a little bit like we're doing mathematical gymnastics for the sake of kind of proving that we can do it. And my hope is that today's lecture and the next couple of lectures will show you that the power of reconfiguring these equations into something that can be written in terms of a small parameter will allow us to establish or develop approximate solutions to those equations. And I think that's one of the things that is hardest for engineers to grapple with. It was hard for me when I was a PhD student. It took me a long time for it to sink in, this idea that I can't actually solve the equation that I want to solve. Like that to me was not I don't feel like people told me that in undergrad. That it was just kind of like you learn the equations, you learn how to solve them, you got the solution, and you kind of moved on. And I don't think anyone ever told me that like actually all the problems you're going to be interested in, the equations are too hard and don't have solutions. And that it was I don't know, kind of a strange thing to realize and to try to not lose hope and build how do we still develop intuition and explain phenomena that we're trying to explain. And so the first thing I will say is that most of the equations you're going to encounter, you can't solve in a closed form exact way. So what do? Well, the answer is oftentimes what you'll do is kind of combine techniques, combine mathematics with experiments, mathematics with simulations, simulations with experiments, to kind of use these kind of approaches from different angles to show and develop an understanding to some problem. And in order to do that from the mathematical perspective, that often means coming up with approximate solutions. And today's class and the next few classes we're going to talk about are kind of formalizing how we come up with approximate solutions. And one of the most common ways that you do that is through the use of perturbation methods. And the idea with this, what is a perturbation method? Well, the idea is you kind of want to find a problem or reduce your problem to something you can solve, and then perturb that solution by kind of adding in a small difference, some small change in the equation you're looking at. And solving this new equation, that's not you're not solving the entire equation, but you're solving some reduced equation plus a small perturbation, some small difference away from the reduced equation. So it'll give you an approximate solution. And you can then perturb it further and take this out to higher and higher orders to get more and more approximations as the small parameter you're interested in changes. So what do I mean by this? What I mean is that we have found or I don't even know if found is the right word. We have a procedure to find dimensionless groups and identify a small parameter. Oh, that's not even close to right. And we're going to, throughout this course, oops, I should use a different epsilon, sorry. Throughout this course, we're going to be referring to that small parameter as epsilon. We did that last class. We developed the small parameter epsilon in the projectile problem, which was the relationship between the height of the projectile and the radius of Earth. And then we found two different types of epsilons, depending on the nature of the problem, for that nonlinear diffusion or the KPP equation. And once we have that small parameter, these approximate methods, and in particular this perturbation method, will allow us to find solutions at different orders of epsilon. So the idea would be, let's simplify the equation and find what the solution would be if epsilon was exactly equal to 0. So it's not only small, it's identically 0. And then we're going to alter that problem and find a solution when epsilon is not exactly 0, but really, really, really small, 10 to the minus 3, something like that, and so on and so forth. There are two types of approaches to perturbation methods. If you recall, at the end of the last class, I said we have two different problems for this reaction diffusion equation. And I said one of them is fairly straightforward to solve, and one of them is quite challenging to solve. Those correspond to the two types of canonical perturbation methods. One is referred to as regular perturbations, which will be the focus of today's lecture, and I think on next Tuesday's lecture, or the next lecture after the homework is discussed. And the second is singular perturbation methods. We'll come back to that. To demonstrate how to use perturbation methods, we're going to start with really, really simple equations. So simple that you learn to solve this equation, I don't know, probably in kindergarten, where we are going to start with a second order polynomial, something that we all know how to solve using the quadratic equation, but we're going to pretend that we don't know how to solve it. It's not a differential equation, it's algebraic, but it's going to be really illustrative in terms of the techniques that we need to use to solve more complicated equations. And then the next time we talk, we'll go back to that projectile problem, and now that we have a small parameter in there, we'll do a regular perturbation to determine how that problem changes as a function of epsilon. So let's start. So we're going to start with an algebraic equation. And the one we're going to use is just a second order polynomial. X squared plus 2 epsilon x minus 1 equals 0. Here's our small parameter. Obviously, we can solve second order polynomials. You may or may not know that there are analytical solutions to third order polynomials and fourth order polynomials. They're quite messy, especially the fourth order polynomial one. And then there is no analytical solution to any algebraic equation of higher than fourth order. And so these techniques can be used in not only for solving differential equations, but for solving algebraic equations. Oftentimes these arise from linear stability analysis, in which you're doing kind of essentially solving linear systems of equations or things that reduce from matrices. And so we often think of, applied math and mechanics being only differential equations, but these algebraic equations can turn up and be useful to solve as well. Okay, so the first thing we can do, is probably not the first thing you would think to do, is that just to kind of illustrate what this equation is doing, we can actually just draw this equation. If we just simply rewrite it as kind of moving over the small term to the other side of the equation, we could have something that looks like x squared minus 1 equals negative 2 epsilon x. Why am I doing that? Well, now I can plot two lines. So I can say, well, I can plot a line for x squared. So we know that's going to, oops, that's not polynomial. There's a polynomial, that's for x squared minus 1. And then we can plot our second line, which is going to be for negative 2 epsilon x. And so this line is going to have a slope that depends on the magnitude of epsilon. And so it'll look something like this. As you may recall, what you're doing when you're solving an equation like this is you're looking to find the roots of that equation, and the roots correspond to where these two lines are intersecting each other. So this is like negative 1, this is positive 1, and these things are intersecting themselves somewhere away from 1 or minus 1. The reason I'm drawing this is not to just kind of illustrate the roots, but it's more to say that the reason this is a regular perturbation problem is that there are two roots, and the number of roots do not change when we take epsilon to 0. So when we take epsilon to 0 in this equation, it's equivalent to taking this green line. I don't know if you can see my pen in the drawing here. It's equivalent to taking this green line and making it parallel to the x-axis, decreasing the slope. And there will be two intersection points between the green line and the parabola, no matter what value of epsilon you choose. And that means there will be two roots, no matter what value of epsilon you choose. And this is what makes this a regular perturbation. The reduced problem, when we take epsilon to 0, has the same number of solutions as the original problem. I'll write that one down. So this is the hallmark of a regular perturbation problem. The simplest way to observe, to kind of determine if you have a regular perturbation problem, is to find the highest order term in your equation in a differential equation that refers to the highest order derivative, and an algebraic equation that refers to the highest order polynomial equation. And if epsilon multiplies the highest order term in that equation, it will be a singular perturbation problem. Otherwise, you'll have a regular perturbation problem. So if I had taken epsilon, and instead of having it multiply this term, if I had taken it and had it multiply this term, this would be a very, very different problem. We will come back and solve that problem. That's a singular perturbation problem. We'll come back to it. Okay. Second order polynomial, this can be solved exactly using the quadratic equation. So let me come down. I'm not going to write out the quadratic equation, but we will show you the exact solution. So this has an analytical solution, which yields x is equal to negative epsilon plus or minus 1 plus epsilon squared. This is great. It's an exact solution. We can use this and run forth and conquer. I'm going to rewrite this equation in such a way that we can see how the solution x depends on epsilon. And I'm going to write it in a way in which it's perhaps a little bit more intuitive. Even if it's not more intuitive, it'll be a way that's going to be useful to us as we develop this perturbation technique. So the way I'm going to do that is I'm going to say, okay, I don't really understand what's happening to x as I vary epsilon. I have this epsilon term out front, and then I have 1 plus the square root. That's conceptually hard for me to think about. So I'm going to say, well, I can use the binomial expansion. This is epsilon we're assuming is small, so we're assuming epsilon squared is less than 1. I'm going to use the binomial expansion to expand this square root term. And that 1 plus epsilon squared through the binomial expansion gives you 1 plus 1/2 epsilon squared minus 1/8 epsilon to the 4th. And then we could keep going if we wanted and add on more and more and more terms, and so on and so forth. If we put that back in and expand, let's see what that looks like. If we put that back in and expand, we would get something like this. X is equal to negative epsilon, that didn't change, plus or minus. And then parentheses, the terms that result from the binomial expansion. So we're replacing the square root term with 1 plus 1/2 epsilon squared minus 1/8 epsilon to the 4th. And we'll do one more step, which is that we'll kind of multiply this thing through. We'll expand. We'll just kind of open up this solution. So that means x is equal to plus or minus 1 minus epsilon plus or minus 1/2 epsilon squared minus or plus. So our plus or minus gets flipped because of the negative sign there. So a minus or plus epsilon to the 4th. Dot, dot, dot. The reason I'm doing this is because now you can see explicitly how x depends on epsilon at each order. So we could really explicitly pull out these things to each order. So at order 1, and this I'm going to use the mathematical symbol, it's basically a capital O, it's usually a little cursive. So at order 1, where I retain only terms magnitude up to 1, discard all epsilon terms. This is the equivalent of setting epsilon to exactly equal to 0. At order 1, we immediately see that x is equal to plus or minus 1. And if you go back to our graph up here, that kind of makes sense, right? If I take epsilon equal to 0, that green line becomes perfectly parallel and it becomes, well, exactly equal to 0. So you just have a line on the x-axis. And so where these things will intercept is at exactly minus 1 and 1. So our two roots when epsilon is equal to 0 is going to be equal to minus 1 or 1. I can look and see how this solution changes as I take an approximation out to order epsilon. So at order epsilon, that means I'm going to retain all terms up to epsilon and discard anything of epsilon to the power higher than 1. So I'm going to throw away this term and just keep these two terms. And so I have, in this case, up to order epsilon, my solution is plus or minus 1 minus epsilon. And order epsilon 2 gives me x is equal to plus or minus 1 minus epsilon plus or minus 1/2 epsilon squared. And we can keep going. Obviously, we have a fourth order term. We could take this expansion out to epsilon, order epsilon to the fourth, and write out the solution that we have above. And we could go to whatever we want. And the full analytical solution would be this taking this series out to infinity. So we haven't done anything yet. We haven't done any perturbation stuff. But we're just literally taking the exact solution and kind of ruining it by approximating it. But this will be helpful because when we do our perturbation method, it'll be really, it's going to give us an answer that's going to look a lot more like this than it is like this. And so your ability to kind of connect those two is important here. I find that the way I connect those two is through visual means. And that's the reason why I wanted to introduce Mathematica here, in part to help us solve the equations, especially when we get to differential equations where there's just a lot of kind of pen and paper work where things can go wrong. But also because we can very quickly and easily graph these things and see how the solutions are changing and behaving. So that's why I kind of wanted to open the door there. Okay. So this is the analytical solution. Now I'd like to get into our approach to approximating a solution. And right now, I have to ask you all to pretend that we don't know the analytical solution. And just pretend that I wrote down this equation, x squared plus 2 epsilon x minus 1 is equal to 0, asked you for solutions, and you didn't know how to solve it. We don't know that there's an analytical solution that exists. How can we approximate the solution? And what we will do, always, what we will always do is start with a simple, powerful guess in the form of Taylor's theorem. If you recall what Taylor's theorem is, it says that if I have a function f of x, I can approximate that function as f of 0, or f at 0, if you will, plus x times the first derivative of our function evaluated at 0. This is technically x over 1 factorial, which is 1. You see it again a little more clearly when I take this to the second order. I would say it's 1 over 2 factorial. It's the Taylor series expansion. X squared, f double prime, evaluated at 0. 1 over 3 factorial, x cubed. Third derivative evaluated at 0, and so on and so forth. This is, since I'm evaluating these things at 0, this is technically the Maclaurin series. You can do this more generally and evaluate it at some point A by inserting kind of like an x minus A in here in terms of where you're taking your series about. Right now, we're going to take it about 0. This is often the case with these perturbation problems because by taking it about 0, as you're going to see in a moment, that's the equivalent of saying take it about epsilon is equal to 0. So in fact, let's rewrite this And instead of writing it in terms of f of x, let's write it in terms of what we want, which is we're going to be using, our function is x of epsilon. And so instead of, this is going to look slightly different, it's going to be evaluating at x at 0 plus epsilon x prime at 0 plus 1/2 epsilon squared x double prime at 0, and so on. And now you can kind of get the hint as to why we rewrote our analytical solution in terms of kind of 1 plus epsilon squared, blah, 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 because now we're going to be using an approximate solution that is in this kind of polynomial type series here. To be really pedantic and careful, I have to point out, and for this particular problem, we're going to solve this in a more general way. Right now, by using the Taylor's theorem in this form, we're assuming that our solution for x has integer powers of epsilon, right? I assumed it's epsilon to the 1 plus epsilon to the 2 plus epsilon to the 3. In general, this is not true. In general, it's not a reasonable assumption. It's not a reasonable assumption for nonlinear problems. In general, assuming that we're going to have some integer sequence for epsilon is not going to work. So what people will typically do is write this in a more general form. And this more general form looks sort of similar. I'm going to change the notation a little bit, and then I'm going to kind of show you how that notation connects back to what we said before. I'm going to change the notation a little bit so that we're going to write x sub 0 or x naught plus epsilon to the alpha, x1 plus epsilon to the beta, x2 there's a few things to note here. One, I just mentioned that I kind of, for the sake of notational simplicity, replace the derivatives and the bracketed notation with just these subscripts. I will go back and show you how this connects to the Taylor's theorem once we solve the problem. So that's just a kind of making things simpler for us to write down while we're doing this. The second thing, you'll notice that we're not assuming integer powers of epsilon. We're just saying it's going to be epsilon to alpha, epsilon to the beta. What we are assuming, though, is that what's referred to as the well-ordering assumption. And that is that the well-ordering assumption states that alpha is less than beta, is less than gamma, and so on and so forth. Which makes sense. If alpha was 1 and beta was 2, we're saying alpha is less than beta, and so on. So that's one of the assumptions we're making. The other thing you might have noticed is that I got rid of our equal sign, and I replaced it with this kind of approximate scales as kind of symbol here. And that's because, in general, our asymptotic expansion does not necessarily have to converge, which is something that is not comfortable for people with a strong mathematical background, that this idea that we could be using an approximate series that's not going to converge if we took an infinite number of terms. Nonetheless, that is true and can still provide useful models for our behavior here, which is why I'm not saying this is equal, because equality would mean if I took an infinite number of terms, I would have the exact solution for x. Okay. Those are our caveats. But this is the idea. This here is what we are assuming is the answer for x to our polynomial equation. When we do a differential equation, we are assuming this is the answer for x. Now, we know epsilon, we don't know alpha and beta, but we're going to determine alpha and beta in the solution process. And the other thing we're going to determine are the coefficients on epsilon, x0, x1, x2. So we're assuming that what I've highlighted in yellow is the solution, and now all we need to do is plug that solution back into our original equation, and then we'll apply some techniques that will allow us to solve for alpha and x0, beta, x1, so on and so forth. So we have to insert this into our equation. So we'll come over here. So recall our equation is x squared plus 2 epsilon x minus 1 equals 0. So first we'll have to deal with this pesky x squared term. To deal with this x squared term, I have to take my solution for x and square it. So I have to take x0 plus epsilon alpha x1 plus epsilon beta x2. I'm squaring it, so I'm going to multiply it by itself. Oh, hold on. I should be careful here. Okay, so we can multiply this thing through here. We can say I'm going to get something that looks like x squared, x0 squared, plus 2 epsilon alpha x0 x1 plus 2 epsilon beta x0 x2 plus epsilon 2 alpha x1 squared plus epsilon 2 beta x2 squared plus some higher order terms. For now, for the sake of simplicity, just to kind of not have to carry around a bunch of extra terms in our equation, we're just going to keep these first two terms in our solution here. So we're just going to keep it up to epsilon to the alpha. So now we have to go over here and that's not what I want to do. Look at our second term. And this one's quite simple because literally all I have to do is rewrite what we had, which is that this is going to become 2 epsilon times x, which we're saying x is x0, plus epsilon alpha x1. And to be consistent, since we truncated the x squared term at epsilon to the alpha, I'm going to truncate this x term at epsilon to the alpha for now. Okay. So going back to our equation and rewriting it in terms of our guess for the solution of x, then I would write x naught squared plus 2 epsilon alpha x naught x1 plus some other terms plus 2 epsilon x naught plus epsilon z alpha x1 plus some higher order terms minus 1 equals 0. And just to be extra clear, this term is my x squared term. And this term is my 2 epsilon x term, and this term is clearly my minus 1 term. So that's our new equation, rewritten in terms of our guess of our solution. Questions as to how we got here. This general procedure is you're going to apply it a bunch of times. We're going to take this form for x, insert it back into our original equation. If it's a polynomial equation, it just means kind of evaluating to whatever order of x that the polynomial equation is to. If it's a differential equation, it's going to mean taking derivatives of it with respect to whatever terms are the independent variables in your equation. And so being able to take this thing, insert it back into our actual equation, and then just kind of simplify it or kind of do the algebra, I guess you'd hear, is going to be a procedure that you follow kind of over and over again. So are there any questions here? No? Yeah?
Actually, yeah. So just to be clear, so we grouped in the 1 over n to the factorial into our x1 term, or we?
Yeah, exactly.
Okay.
Yeah, so that's the part I'll come back to at the end. Not only are we kind of taking that x subscript term as our derivative, it's also got the prefactor that comes from the 1 over I factorial. And I'll show that more explicitly at the end, how that connects back. All right, so let's solve this equation now. So what we're going to do is, so step 1 is we write down our guess, comes from Taylor's theory. Step 2 is we insert our guess into our equation. And step 3 is that we're going to start at order 1 and solve for our first constant. And at order 1, our first constant is, if we order 1 means I take epsilon to be exactly equal to 0. So if I take epsilon to be equal to 0, this term goes away, this term goes away, and I'm left with just x naught squared. Okay, so let's come over here. I guess do it here. So at order 1, we let epsilon go to 0. Our equation simplifies dramatically. It becomes x naught squared. Oops. Minus 1 equals 0. And then pretty simply, x naught is equal to plus or minus 1. Now let's just do a sanity check, so we're all on the same page here. Our solution to the problem is this. This is the answer. And once we determine each of these terms, then we have the answer to higher and higher levels of approximation. So what I mean by that is we just found out that x naught is plus or minus 1. And so if we look at our order 1 solution, it says that x at order 1 or order epsilon 0 is going to be equal to plus or minus 1. So we can go back And our analytical solution tells us that at order 1, x is equal to plus or minus 1. So by guessing our solution, plugging it in, and solving for our unknown coefficient x naught, we found the order 1 solution, the exact solution to our problem. We keep going, and we get more better and better approximation for our answer. So we've already got the order 1 solution, not bad. We're good? Questions? Okay. Okay, so now we have to insert this back into our equation. This here, another way to think of this is that x squared is equal to 1. And so if x squared is equal to 1, if I put this back into our equation, if x squared is equal to positive 1 and this is negative 1, our equation simplifies and I'm just left with this here. Okay. So I put in x naught back into our equation, and our equation now becomes plus or minus, actually I'm going to write it in orange for consistency, sorry. Our equation now becomes plus or minus 2 epsilon to the alpha times x1 plus dot, 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 2 epsilon plus or minus 1 plus epsilon to the alpha x1 equals 0. The x naught squared term goes away, the minus 1 term goes away because they're equivalent to each other, or they kind of annihilate each other, I guess. And so now this is the equation that we're looking to solve. And before we can go to the next step and solve for x1, which is the next coefficient we don't know, we have to figure out what alpha is. And this equation kind of presents a problem here. So let me expand it. So I'm just going to multiply through to make it more clear. So I'm going to say this term stays the same. And then this becomes plus or minus 2 epsilon plus 2 epsilon to the 1 plus alpha times x1 equals 0. Couple of notes. This term is of higher order. So right now, to the next order, we're looking for epsilon to the alpha. We don't know what alpha is yet, but no matter what alpha is, this term will be higher order because it's 1 plus alpha. Okay, so now we have a problem. But this problem is going to be the way that we resolve our unknown exponent alpha. The problem is that I have an equation here that to each order has to be mathematically valid, which means I should be able to discard terms of order higher than epsilon to the alpha and have a mathematically consistent equation. So I should be able to throw this term out and have an equation that this term plus this term equals 0. The problem is I can't add these two terms together so that they annihilate each other and become equal to 0 unless epsilon, the two epsilons are of the same order. So on the first term, I have epsilon to the alpha, and the second term I have epsilon to the 1. And the only way that I can add these terms together so that they cancel out to be equal to 0 is if alpha is equal to 1. So let me highlight this. So I want to take this term and combine it with this term to get 0. And the only way to do that is if I can add these two terms together. Alpha has to equal 1 so that I have a mathematically consistent equation. So the equation told us exactly what the value of our unknown exponent is. We didn't have to guess. We didn't have to assume it was integer powers. We found it out in the process. I'll be perfectly honest with you. If I'm approaching a problem like this that I'm using to solve something on my own, I am lazy and will just assume it's integer powers, solve it through, and then see if it works compared to some numerical solution or some experimental values. And if it doesn't, I'll go back and try to find what the appropriate powers that my expansion should be. So what we're going to do throughout this course is, in a lot of cases, we're going to assume that our Taylor series expansion can be used with integer powers, and then if it breaks down, we can go back and do it over. I'm doing it now just to show you how you can do it in this more general case to determine what alpha and beta are. But oftentimes I'll just assume it's integer powers, and if it doesn't work, I'll go back and revisit it in a more general form. So your mileage may vary, and you might approach it differently. But okay, so now we're good. Now we know x naught and we know alpha, so we can solve this equation up to the next order. So we can go, oops. To order epsilon. And our equation to order epsilon means discard any terms that are of higher order than epsilon. So only keep terms to order epsilon. And so that means we can keep 2, plus or minus 2, epsilon, x1, plus or minus 2, epsilon, equals 0. What happens is our epsilons cancel, 2's cancel, so do our plus or minuses, and we're left with that x1 equals -1. This will always happen if you do your ordering and your grouping correctly. Your epsilons are always going to cancel at that order. So sometimes you'll see people write this leaving out the epsilons because each term that you're keeping should only contain the epsilons that you're evaluating at, and so they're going to cancel out. But I'm writing it here just to be extra clear. Okay, so now we have our solution to x1. So now we have something that says, okay, let's come back over here. For our particular problem, we have that x of epsilon is plus or minus 1 minus epsilon. And to be perfectly, or to be more accurate, what you would say is, then this is plus order epsilon squared. So we expect there to be, this is not the exact solution, we expect that if we continue this approximation out to order epsilon squared, we'd get closer. And so again, we can see, this is up to order 1, this is up to order epsilon, that's the highest level term we're keeping, and up to order epsilon, our approximate equation and our analytical equation are equivalent. So we are approximating the solution to our problem term by term. The more terms we keep, the larger value of epsilon our approximation will be accurate for. And we just continue. We just continue forward. We can do this ad nauseum. We can say, okay, well, now what do I need to do? Well, now I need to go back and evaluate what my equation is. Now knowing epsilon x naught, x1, and alpha. And to do that, I'm going to get something like, my new equation becomes plus or minus 2 epsilon to the beta, x2 plus epsilon squared plus some stuff, plus 2 epsilon times negative epsilon, epsilon to the beta, x2. So I had to go back, just to be perfectly clear, I had to go back up to here. And initially I only kept these first 2 terms. Now if we're going to go to higher order, we have to keep terms that include beta. And so I've done that, keeping terms that include beta here, and I've also, when evaluating here, kept the term that includes beta here. So I've said, now let's take this to be 2 epsilon x naught plus alpha, epsilon to the alpha x1 plus epsilon to the beta x2. And so I'm taking this equation, and I'm including all terms up to epsilon to the beta. And that's how I got here. And again, you're going to see the same problem arise. And so I'm going to expand this out. The first term stays the same. This will be what, minus 2 epsilon squared. What's left of that? This is going to be plus 2 epsilon 2 plus beta x2 equals 0. And again, you see the same problem emerges. I need to add all of my epsilon squared terms and have them equal 0. So I should be able to, again, discard any of the higher order terms and have a mathematically consistent equation. So this term plus this term have to equal 0. They clearly don't. You can't. Negative 2 plus 1 doesn't equal 0. So the only option is for this term to help us annihilate those 2 terms. And the only way that these 3 terms can be added together is if the exponent on epsilon is the same. And so therefore, beta has to equal 2. Then I can add my equations together, and then I can solve. So again, we've used just this idea of kind of having these homogeneous equations that we're adding terms of equivalent order together to find out what our exponent is. And then once again, now that we know what beta is, we can solve our problem out to order epsilon squared, and we'll end up with plus or minus 2 epsilon squared x2 plus epsilon squared minus 2 epsilon squared equals 0. Again, you see the same thing as I mentioned. You're going to find that when you take these things to this order, these epsilons should cancel, 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 and then we can solve and find that x2 is equal to plus or minus 1/2. I'm going to come back over here. Sorry, I guess I skipped one. So let me first take this thing down and write out that x of epsilon is equal to plus or minus 1 plus order epsilon terms. And now we can do this again. X of epsilon is equal to plus or minus 1 minus epsilon. Now we have epsilon to the beta. Beta is equal to 2. And my x2 is plus or minus 1/2. So I'm going to end up with plus or minus 1/2 epsilon squared plus order epsilon cubed. And again, we can check our solution, right? And we see that to order epsilon squared, our analytical solution is equivalent to our approximate solution. And this will continue. This is an asymptotic expansion of the solution for x as epsilon goes to 0. The larger epsilon is in your problem. Remember, epsilon is a dimensionless parameter. In the case of the projectile problem, it's the ratio of the height of the projectile to the radius of Earth. You often will know what value of epsilon you're interested in. And these approximations are going to, the magnitude of epsilon is going to tell you kind of how much of an expansion you need to keep to approximate your solution. And I'll show you that in a moment, if that's not clear. There was one more thing before I go on. I kind of want to just show you. I mentioned that we, like, for simplicity's sake, changed our notation. Let me just show you that here. So if we take this as our solution, if we take, I should write this in a different color. Let's do this in green here. So if we take this, and if I say let's evaluate dx, d epsilon, then I would get -1 plus epsilon as my dx, d epsilon. And if you recall, in our Taylor series expansion, sorry, I'm going to scroll up here. Where did it go? Oh, it's right there. If you recall here, this is x prime evaluated at epsilon is equal to 0. Okay, so this is x prime. So I need to evaluate that at epsilon is equal to 0. So let's come back down. So if I want to evaluate that at epsilon is equal to 0, I can say, okay, the thing I'm interested in, going back to the Taylor series expansion, is the value of x prime evaluated at epsilon is equal to 0. That means take the derivative of x with respect to epsilon and evaluate it at epsilon is equal to 0. And that is equal to -1. And that's what we defined as x sub 1. So the prefactor, as you mentioned, is kind of baked in there. You could do this and check what I'm doing at higher orders. You can say, okay, well, what am I saying? 1/2 x double prime at evaluated epsilon is equal to 0 is equal to 1/2 second derivative of x with respect to epsilon. The second derivative of x with respect to epsilon is just going to be 1. 1 times 1/2 is equal to 1/2. And then we define that as x sub 2. This is just if you're a little bit lost right now, this is just kind of a consistency check. I said up here that I was going to simplify our notation by taking kind of this term here, or I guess it's even easier if I say like this term and just call it x2. So 1/2 times the second derivative of x double prime evaluated at 0. I just said let's call it x2. And this just kind of shows we defined x2 as 1/2 the second derivative of x with respect to epsilon, which is exactly equal to 1/2. So that was just a notational switch to make things easier, but it ends up giving you the same kind of result. Okay, questions?
I have a quick question. What happens to your 2 epsilon 1 plus alpha term? Like, did I miss where that eventually ended up, or does it go away somehow?
That's a good question. So remember that we are assuming that we know the answer. We know that x is this. So we took this and we inserted it into this equation. And so when we take this and insert it into here, then we end up with this orange thing, where this term here is x squared. And now look, I have 2 epsilon times x, where x here is x here. And then I have my minus 1 over here. So my 2 epsilon x term is this. It's wherever I see kind of 2 epsilon times my stuff here. And so at this level, we now know what x1 is. So x1 becomes plus or minus 1, but we don't know what this is. And at this level, we know what epsilon alpha x1 is, negative epsilon. And so we have this term left over. So this is our assumed solution for x. And what we do is we take our assumed solution for x and we insert it into our equation. And so our 2 epsilon x term just kind of got looking messy due to algebra, but it's right here. Does that help? Am I answering?
Sorry, I don't think I was totally clear with what I was asking. After you solve for x naught equals plus or minus 1, and then in that line where you have alpha equals 1, like kind of below it, there's this 2e to the 2 epsilon to the 1 plus alpha term to the x1. Does that just, I guess I'm just not seeing where that ends up, if anywhere, in kind of your solution when you wrote out your like x at epsilon with x of epsilon at order epsilon to the 1.
Yeah, good question. I think it ends up here, because if this term here is, where does it go? Do I have a sign change?
It's epsilon to the 2, right?
Oh, it gets squared. Yeah. What?
Is it 2 plus beta?
No, that's a new term. So this term becomes, so because we know alpha is equal to 1, this becomes 2 times epsilon squared times x1. And now I'm wondering if I'm supposed to actually have x1 squared. So I think the short answer is this term becomes 2 epsilon squared, because we know alpha is equal to 1. So 1 plus 1 is 2, 2 epsilon squared times x1. And so I think this term becomes this term, epsilon squared. Where did the 2 go? No, sorry, this term. Yeah, it becomes this term.
Oh, okay. So you don't see it until you do your like second order.
Yeah, to be fair, I could have taken this term and then rewritten it. That's a good question. So I could have gone here and said, so I could have said, well, now that we know alpha, then this thing becomes 2 epsilon squared x1 plus, what do I have? Plus or minus 2 epsilon plus 2 epsilon squared x1 plus some other terms equals 0. And then this is the
first one's just the power of 1.
Yeah, what happened? Alpha's 1, sorry. I was like, wait, what do I have? Yeah, okay, thank you. Yeah, perfect. So now this term, we said now that we have this green equation, now let's solve this green equation up to order epsilon, so discard epsilon higher terms. And so then that's how we got here. So this term is this term, and this term is this term, and because we're only considering solutions for up to order epsilon, we threw away this term, and then we just solved like these two things equal 0. And then at the next order, this one comes back. And this one comes back because at the next order, this term here, I'm going to use all the colors today. This term, we know that x1 is equal to -1. And so this term becomes can I do this? That one. Because x1 is equal to -1. Does that help? Is that
Yeah, that clears it up. Thank you.
cool? All right. Here's my plan. Let me know if this makes sense. I would like to take a break for a minute, do a rapid crash course in how to use Mathematica, and then resolve this thing again in Mathematica to give you a kind of a visual understanding of what's happening and what it means to have approximate solutions to different orders in epsilon. If you have Mathematica, then go to my course website. I don't know where that is. It's probably over here somewhere. Hopefully. If you already have installed Mathematica, if you haven't installed Mathematica, you should be able to go, and I have the link to the student version here. If you, nope. But if you have it, then you can go there and you can download 2 Mathematica files, and that's what we're going to go through right now. This first one is just an introduction to Mathematica. If you know how to use Mathematica, this might or might not be useful. I try to get into some more advanced stuff that's buried in there, so you might find it useful. And otherwise, this is the regular perturbation. We're going to literally do this problem again, and I'm going to show you how to do it in Mathematica. I find it to be more useful than doing it by pen and paper. So take like a couple minutes, get those loaded up, and then we'll come back.
Yeah.
No.
Yeah, and the outlet is not working.
Did the outlet not work?
It's not working. I tried it last night when we had the gas speaker.
Yeah.
No more.
Not even the wall ones?
I haven't tried, but
All of them are dead?
I mean, it's not.
yeah, I think they only enabled the outlets around.
Really?
Is this one of the rooms I got redone?
Yeah.
Yeah.
It used to be blackboards over here. I miss them. I miss them mightily, but I guess you can't use blackboards anymore, so.
Why?
Well, because of the learning from anywhere.
Oh, yeah.
Yeah, that's a, yeah.
Yeah.
Normally I would be using them, but.
I saw Stefano couldn't get his thing to share on his lectures, so he was writing on the whiteboard.
That's hard, yeah.
I think you lost something on the chat.
Huh? Those are from earlier, I think? Yeah. Okay, cool. Thanks.
What was the password for the Zoom link? Because I was running late today and tried to open it up. Give a little, but I don't get the password.
It's just the force number. You don't even want to say it.
Well, they're on YouTube, so. Sorry.
What?
All right. Let me give you a crash course on how to use Mathematica. I would encourage you to play with it on your own. outside of this class because we're going to use it a lot coming forward. And I think if you just use it when we're doing it here, it probably will not be that pleasant. I'm going to start a new notebook. So these are called notebooks. They have cells. You just start typing, and it starts into a cell. This is the thing that you just downloaded. If you want, I'm going to write it on my own in my blank notebook. So if you want to follow along, you can do what I'm doing. So to use Mathematica, you enter something that you want to do. So if I want to just do some basic math, 14.6 plus 27, and I hit Shift Enter to evaluate, and it gives me a number. Lovely. To multiply, you can either use a space bar, so I can do 5 space 7, Shift Enter is 35, or I can do 5 asterisk 7, also 35. Division, you can do 2 things for division as well. I can either do 1/5, or I can do 1, and I can hit, at least on a Mac, it is Control, the slash symbol, and then I have a fraction. So I can do 1/5, and then I get the same thing out. You might be annoyed that you have 1/5, and you're like, I can't remember what fraction that is. I actually want you to give me the number. So you can do one of 2 things. You can type 1/5, and then you can do /n, and it says give me a number. The n is a function, and that function literally means give me the number. So I can write in Mathematica, and I want to show this again in a second, all functions use square brackets. So I can write n square brackets, and inside there I have to give it something. So I can say, well, give me the number of 1/5, give me a numerical form, it's 0.2. It's pretty straightforward. So like I just said, functions in Mathematica have capital letters, like their in-house functions have capital letters, and they take square brackets. You can't use square brackets for an equation. You can only use parentheses. So functions work like this. I say, give me the sine of 3. Oh, it doesn't do anything. It's going to keep it in kind of that form unless I say, give me it as a number, and then I get a number out of it. I can use, one of the powers of Mathematica is the ability to use kind of symbolic notation, essentially to make your equations look like your equations on your pen and paper. So I might want to write sine of pi over 2. I hit the escape key, and that brings up those 3 little dots down here. I can type pi, and it shows up down there. I hit enter, it comes back. And then I can make a fraction, pi over 2. It didn't work. You know why? Because I put parentheses in the wrong spot. Go over there, and now it works. Yeah.
The function like n square bracket, sine square bracket.
Those are functions. Sorry.
So can I put the function in the function, like n square bracket?
Oh, let's find out.
Good
Good question. And I don't know.
Oh, I think the other way around.
Oh yeah, for sure. You can definitely do like n.
Yeah, right.
Yep, definitely. Yep. It gives you a period because it's saying it's actually like a numerical. It's like a floating point number, even though it's an integer. You can be really specific about n too. You can say, give me the number for pi. Oops, pi, and I want it up to 37 decimal places, and it'll spit out pi at 37 decimal places. Just like at all MATLAB, C++ code, you can suppress output by just putting a semicolon at the end. Doesn't do anything. That's not useful for something like that, but if something like defining variables, defining functions, it's useful for. Other functions that are important are clearing things. So you can, if you define a variable, you can use clear to clear that variable. I already did this. You can write special characters by typing escape, the character you want. So I can go escape theta. Theta shows up. I hit escape again. Or I can do escape, I don't know, row, and I can hit enter if it shows up. It's the same thing. Something that's going to be very useful for us is defining our own functions. So if I want to write f of x, I write f. If my f is my new function, that's lowercase because I'm defining it. So I'm going to say f is my function. I want it to take one parameter. I want it to take x. So it's f square bracket x, and then you have to give it this underscore. I don't exactly remember why. I think it has to do with the fact that it's Mathematica's way of knowing that it's looking for x on the other side of the equation. And then you can either write this as equals something, so x squared plus 3x minus 4. Oftentimes in this class, I will write it with a slightly different notation, which is colon equals, which basically says, hey, Mathematica, store this function, but don't evaluate it. I'll talk about why that's useful in a minute. It's useful for any time you're doing like a series expansion, where you want to define a series expansion, but you don't want to tell it what order you want. You know, if you have like a series expansion that's from like summation from x is equal to 1 to infinity, you're going to say, you're going to define a function, and then you might take it to, instead of infinity, you might take it to 20. Doesn't matter. Just know that nothing really changes too differently, but this notation basically says set it, but don't evaluate this function. But now that I have this function, I can take f and I can stick a number in there and I get something out. So I don't know, f of 4. So if x is equal to 4, it plugs 4 in for x there, and I get a number out. Right? That's probably right. There's a couple other things in here that are useful to you as you start playing with things. So parentheses are how you do like your nested equations. So you would say like, oh, I want to do like x times 5 minus x and times 6x squared, I don't know, plus 2. Parentheses are for this. Square brackets are for functions. And curly braces are for lists. And Mathematica deals with everything as a list. That's the way this language works. And this is where most people get a little bit confused. But we'll work through it together. So to Mathematica, if you ask for a solution, it's going to give you the solution as a list of solutions. So if you have a system of equations and you're solving like 4 linear equations with 4 unknowns, it's going to give you a list of those 4 solutions. Lists are what Mathematica uses for vectors. So in Mathematica, a vector is a list. A tensor is a list, and so on and so forth. And so I can define a vector as v is my vector, and it's going to have curly braces, and so this would be like 3, 6, 2. That's a vector x, y, z. And then I can do things to that vector like you do anything else. I can do v squared. So what happens if I square my vector? Nothing, apparently. What did I do wrong? Thank you. That didn't work. There we go. I don't know what happened. It just freaked out. So that works, right? It squared each of the terms individually. I can call things, it's similar, you're calling an element of a list. And so this notation is a little bit tricky, but say if I want to take v and I want to get the 3rd item of my list, I basically say, give me, and it's double square brackets. I don't know why, but it is. It's just double square brackets. So v double square brackets of 3 is going to give me the 3rd item of my list. Hopefully that's 2, and yes it is. So for a tensor is just kind of a list of lists. So a tensor might be like various rows and columns. So I could take my tensor and say that that's going to be equal to a comma b, comma b, comma c. And that to me is not very intuitive. So what I often do is I say, okay, if that's my tensor, can you show it to me looking like a matrix? And then now it looks like a matrix. And also, you can also do matrix form, T, because it's function, same exact thing. I'm going very fast. Is this okay? Are people following? Okay. For calculus, you can, well, we already have a function, right? So we can take our function. So remember we have f of x. What's f of x? Oh, where did it go? Oh, yeah, that's all right. Wait, what is it? Let's find that again. So what's f of x? That thing. So I can take a derivative of f of x.
What did you just do there with forcing it to display the actual algebraic form instead of just displaying f of x again at the output line?
So you know how it kind of was being annoying when I asked for b squared and it just kind of sat there and then said b squared? It looked like it basically crashed and lost all my definitions. So I went back and redefined my function by just hitting it again, essentially. So for some reason, this thing crashed and it lost everything I had in there. So I just redefined f of x, and then when I ran it, it came out. So that probably didn't happen to any of you. I think that was just on my computer being weird.
How can you see the list of things that we define?
Yeah, great question. To see the list of things that you define, you use this thing. It's a super annoying notation that I never ever remember, but it is what it is. Mathematica, I have a very strong love-hate relationship with, so you'll see that over the course.
What happens when you have a series of dependencies? Like, for example, what you just redefined, say, on the input line 5 and input line 6. Input line 5 was dependent on, say, the function, and then input line 6 was dependent on input line 5. Is that just, you shouldn't do that in Mathematica, or does that make sense what I'm asking?
I don't know if I totally follow.
So like input line 5 was maybe 3 times f of x, and then input line 6 was x times whatever you defined in input line 5.
So you can do that, and that's usually frowned upon. You would do it like this, where this symbol means give me the last output. And so if I took 3 times this symbol, it's going to take 3 times this thing. So let's see what happens. Yeah, 3 times that. It's generally frowned upon because if you like go down in your notebook and do something else, like no matter what you do, the percentage symbol is the last output. So I would say I never use that notation because it almost always screws up my notepad, or I screwed up my notepad because of that. But you can deal with you can use kind of implicit dependencies, but it's iffy. So this is a derivative. A cleaner notation for derivative is to take f prime of x, starts to look like your math again, and that's the same derivative as before. F double prime. 2, so nice, you can do calculus. You can integrate f of x, and here it's going to give me an indefinite integral. For some reason, it really is actually giving you like an antiderivative. It's not giving you those unknown constants. You can kind of force it to. We won't worry about that for now. I can answer a lot more of these questions as they crop up. I just kind of want to give you a crash course in this. But I can do a definite integral in the same way. I just do integrate x from -2 to 7, and I get a number. And that would be your definite integral. What's really powerful for us is to say solve equations. So I can say solve f of x is equal to, let's say if f of x is equal to 7, what's x? F of x was a second order polynomial, so I'm going to get 2 solutions. Mathematica is going to spit those 2 solutions out as a list. So this is a list with 2 entries, each of which is a list. And here's what you're going to see that's going to confuse you, I'm sure. Mathematica deals with 2 things that confuse people. One is lists, and the second is it says, it gives kind of rules as an output, or like replacement values. So it says, this you can literally read as, replace x with this thing, and that's one solution to your equation. or x can be replaced by this thing, and that's one solution to your equation. That is something that I'm certain will annoy you, but bear with me on it, and I'll kind of show you more going forward. The nice thing is Mathematica can easily handle systems of equations just by giving the systems of equations. You give it to it as a list. So here's a list of equations. This is one equation, x plus 2y. This is the second equation. They're separated by a comma, and you know it's a list because it's in a curly brace. And I'm solving for my two unknowns, x and y, and then it gives you a list as your output for x and y. For equations that can't be solved, there's a bunch of different ways you can solve things in Mathematica. This is something that can be solved analytically. For something that cannot be solved analytically, you might be interested in finding, for instance, the root. So find root of, say, cosine of x is equal to x. I'm looking for it with a guess of x around 0. And it's that. Find root. Remember what we just did, the algebraic plotting where we plotted the curve of the parabola and the curve of the line. Find root is basically doing that. It's going to plot cosine of x. It's going to plot x. It's going to see where they intercept, and then it's going to give you the root closest to the one that you asked for, which in this case was close to 0. To solve differential equations, you don't use solve, you use dsolve, which is differential equation solver. And you give it a list of equations that you want to solve. In this case, I gave it an equation and some boundary conditions, and I told it what function I want to solve and for what dependent variable, and it could solve a whole host of differential equations that are kind of a pain to solve. So dsolve solves differential equations, and then we'll come back to this, so don't worry, I'm rushing here. We'll come back to this when we need it. It'll be next class. NDSolve will numerically solve a differential equation. I think it implicitly uses Newton's method. But I'll come back to, we're going to do a bunch of dsolve and NDSolve, so don't worry about that for now. If you want to play with it, you can. And lastly, you can plot stuff really easily. So you can just say, hey, plot sine of x. From x is equal to 0 to 3 pi. And then it sets a plot there. And I gave a bunch of different example plots over here about all the fancy things you can do. Log, 3D plots, how to plot data. You can play with this on your own time. There's lots of other stuff you can do. And I will kind of go through it as needed. But this should just give you a very, very basic overview of what we're doing. And with the time left, I want to jump to that regular perturbation notebook just so I can sort of show you how I can solve these, and I would encourage you to go through it on your own. But also to show you, give you a visual understanding of what we're actually doing here. So I'm going to abruptly switch. We could chat on office hours or at other times. I'm sure there'll be lots of questions about Mathematica, and I'm happy to help. We'll be using it a lot, and we'll be using it in class. So you'll become proficient at this thing by the end. Okay, so here's what I want to do. This is the other notebook that's on the website. You can download it. And what I did is I defined a function. And I defined that function. This is the exact function that we already defined. It's our polynomial, x squared plus 2 epsilon x minus 1. In this case, I took my function and made it a function of both x and epsilon. It doesn't really matter. This will be useful for us. You can plug in different polynomials here if you want, and you can see how this thing changes. First, let's show you how to analytically solve this equation. So you would say, I'm going to basically expand this ugly thing. So first I'm going to say solve. Oops, I should run this, shouldn't I? So I'm going to say solve f of x, epsilon, is equal to 0, because that's the form of our polynomial equation. solve for x. And you'll see it gives me a list of stuff here. And then here, I'm just using some notation that says replace x with my list of solutions. So I do this. Put it this way: if you want to get rid of this annoying x arrow, you type this, and that gets rid of it. And then I save that as a variable solve. The reason I'm doing that is I can plot the analytical solution, and here you go. So here's the analytical solution of our problem. I have two curves. Makes sense. I have two solutions. These curves, the blue one is down here, the orange one's up here. And the first thing I want you to see is something that matches your intuition of what we've already solved, and that is at epsilon is equal to 0, our solutions are at epsilon equals 0, 1, and -1. All right, so let's approximate. Let's do this. Oops. Let's do exactly what we did in our notebook. And here's what I'm going to do here. I'm going to say, give me a generic power series expansion, epsilon up to order 2. So series is Mathematica's way of saying Taylor series. So give me a series expansion of x of epsilon, and I get something that looks like what we just found, right? It's Taylor series. And now you can see that it's got that mathematical notation there of order epsilon cubed, which is saying that this is plus some terms here that we've neglected because you only asked me to give it to up to order 2. I can, if I say I don't want to have that annoying thing there because I don't know what to do with it, I can say give this to me in a normal form, so get rid of that annoying thing, and all normal does is throw away that order term. So all I did is I wrote a function that allows me to figure out what the expansion is to whatever order n I want. So if I want, so for instance, if I want to take our expansion out to second order, I get that thing. If I want to take it out to first order, I get that. If I want to take it out to fifth order, I get something awful. But this allows me to play with my expansion to whatever order I want. All I'm doing is resolving the same problem we did before. So at order 1, all we do is I say, give me the expansion up to 0th order. It starts counting with 0. And the expansion up to 0th order is just this first term, x naught, x at 0. And here's the thing that's key here. So I want to ask it to solve my equation, solve my polynomial. And instead of x, I'm going to put my expansion term in there. I'm going to put x naught in there. Because to first order, x is equal to x naught, right? To first order, x is equal to x naught. So if I put in f of x naught, and I take epsilon as exactly 0, and I ask it to solve for x naught, and what I get is that there are two options. So when we did it by hand, we got plus or minus 1. Mathematica is going to give you two solutions, -1 and 1 in a list. And then all I do is I insert our solution back into our problem, which doesn't really do anything because it's just x is equal to -1 or +1. But here's why I wanted to do this, just to visually give you this example. So don't worry about the syntax right now. I want you to just focus on what's happening to our solution as we go to higher and higher orders. So don't worry about the Mathematica. We can sort that out later. For right now, if I plot this, I can see that my order 1 solution gets the exact right answer when epsilon is equal to 0, and then does a pretty bad job when I get further away from epsilon in terms of either negative or positive. If I go negative, my approximate solution always under predicts the solution, and opposite wise if I go positive. So I'm going to just go to a higher order just so you can see what's happening to the solution. Again, don't worry about this Mathematica. Do this outside of class, right now I want you to just focus on how we plot this and what we're seeing. Okay. Now in my graph here, can everyone see this? Let me make this bigger. Now in my graph here, I have the order 1 solution and the order epsilon solution. And now you can start to see that the order epsilon solution does a pretty good job with the analytical solution out to about epsilon is equal to 0.1 or 0.2. And then it starts to deviate. Here again, it's below. Here it's also below. And it's under predicting what x is going to be equal to as I get further away. So my order epsilon solution provides a pretty good prediction for what the solution to x is up to about epsilon is equal to plus or minus, I think 0.1 or 0.2 here. Or here I say 0.25. So I can keep going. And you can see what's happened to our approximation. You see how we get closer. Again, don't worry about the Mathematica code right now. Try to play with it later to see if it makes any sense. But now you can see, I don't know, hopefully you can see, my analytical solution is this thick line here. My epsilon to the second order solution is this dashed dotted line up here, which is doing a really good job of predicting our solution up to order epsilon is equal to, say, 1/2 and -1/2. Maybe a little bit less. No, I think that's pretty fair. 1/2 to -1/2. But it's actually doing quite well, almost up to order of epsilon is equal to 1. And this is where you as the modeler in here can decide, like, oh, I know roughly what epsilon is. Epsilon's going to be a ratio of physical parameters in your problem. Maybe it's going to be a ratio of the length scale to the diffusion coefficient, or the height of the projectile to the radius of Earth. I know roughly what that value is, and so therefore I know kind of how good my approximation needs to be. If epsilon is never going to be greater than 0.5, I don't maybe even need to go to order epsilon squared in my approximation to come up with a decent model for it. And for this system of equations, it's not that hard to go out to higher and higher orders, but for other problems, it can be quite tedious. Mathematica is incredibly powerful, and you can do this thing if you want to play with it. Down here, you can kind of play with all the some various code that I have to show how you can generate solutions to whatever order you want. But the takeaway I want you to have here is just to see, okay, here's how my approximation is doing compared to the analytical solution as I increase or decrease epsilon away from 0. And as I add higher and higher terms, it's going to keep switching between underestimating it, overestimating it, underestimating it, overestimating it, but getting closer and closer each time. I would encourage you to go through both of these Mathematica notebooks and see if you understand what it is I'm doing. And if not, then we should chat either in class or in office hours to kind of help break down. I tried to annotate it and give you notes, but as you know, with this type of stuff, you kind of have to get in there and play with these things to actually be able to ensure that you know what you're doing. A nice thing to do would be to create your own notebook and try to solve this problem out to order epsilon 1 or order epsilon squared on your own, and kind of reflecting back and forth between what I did just to see different ways that you can use it. But the main purpose of this was to A, get you introduced to Mathematica because we're going to be using it going forward, and B, to give you a visual understanding of what's happening with our approximate solution as we go to higher and higher terms in our expansion. Any questions?
I have a question.
Yeah.
So in general case, do we know the analytical solution all the time? Because if you don't know the analytical
Definitely not.
solution, how can you know, like, up to how much order we should expect it to?
Sure. So the question is, in general, do we know the analytical solution? And the answer is no. And to be honest, if you know the analytical solution, you shouldn't be doing this.
Yeah,
You don't need it. Oftentimes, for simpler problems, you can pretty quickly get the numerical solution. So the downside to the numerical solution is you're going to get the numerical solution for very specific parameter choices. You're not going to get it in terms of epsilon. You're going to get it for epsilon is equal to 0.12. And if you want to solve it for epsilon is equal to 0.13, you got to resolve it again. for epsilon is equal to 0.13 and do that over and over again for every epsilon. So that's the downside of the numerical solution. However, the numerical solution can be a really great way for us to compare our analytical solution, sorry, our approximate solution to something, see how it's doing. The broader question you're asking is like, how do I know how many terms I need to keep? It comes down to two things. One is, how small is the small parameter in your problem? That you should know. You should know your small parameter. It's going to be something physical. You should know what order it is. Is it order 10 to the minus 5 or is it order 0.2? That'll tell you, and the larger that value is, the more terms you're going to need to keep. The second thing is this should not be used, any of these approximate methods should not be used on their own. They need to be used in conjunction with something else, whether it is numerical solutions, whether it's computational like simulations, experimental data. You're generally not doing this in a vacuum, but what you might be doing is saying like, well, okay, my approximate model says that I would expect that my equation goes quadratically with epsilon, and so let me do some experiments and see if my data goes quadratically with epsilon. You, in general, won't use this thing on your own. You, in general, won't have an analytical solution. Even a numerical solution might be tricky at times, and so you need something else to kind of ground you and see if you're doing things well or not, and see if your model, and it's like anything else. You're creating a model. At the end of the day, this course is trying to help you learn how to create a model, and a model is always wrong, but sometimes useful. And so you only can determine if it's useful by comparing it with things that, or making predictions with it, or comparing it with data that you have. All right, we're over time. Thank you, everyone. I know I rushed through the Mathematica stuff at the end, but we can come back and circle back to it as needed. And I'll try to post all this stuff up. We have homework due on Tuesday. Hopefully you all got that email. And we're going to plan to have you all go through it in class again like we did in Tuesday in class. So have a nice weekend, and see you all next week.